Okay, let's dive into something that's, well, it's really on everyone's mind these days, artificial intelligence. I mean, it's not some distant future concept anymore, right?
Not at all. It's deeply woven into our daily lives, really quite intricately.
Yeah, intricately. But, with that incredible power, there's this other side, this growing, urgent question about data, privacy. How do we protect our personal stuff, our private info, even company secrets, when these AI models learn from, well, pretty much everything?
Exactly.
So imagine an AI that's not just, powerful, but actually designed from the get-go to fiercely protect sensitive info. That's kind of the promise we're exploring today. We're looking at Google's VaultGemma 1B.
That's right. And this isn't just like another small update, VaultGemma 1B. It really represents a fundamental shift. It's a reimagining of how these large language models can even be built. It takes this idea, privacy by design, which has been mostly theory, and makes it, practical. And what's really significant, I think, is that it's the largest open weight model out there. We're talking 1.04 billion parameters. That was trained entirely from scratch using full differential privacy. That's a huge deal.
Wow, okay. Sets a new benchmark there.
A very high new benchmark, yeah, for the whole industry.
Got it. And so our mission here for this deep dive is really to give you a shortcut, a way to get quickly up to speed on this really critical innovation. We're going to unpack what VaultGemma actually is, get into the, let's say, ingenious methods Google used for privacy. We'll look at the trade-offs, because there always are trade-offs.
Always.
Explore why Google might be doing this strategically, and hear what the tech community is saying. So by the end, you should have a really clear picture. It's potential, but also, its limits. Okay, so let's start right at the beginning. The why. Why is VaultGemma, needed right now? The core problem, as I understand it, is this thing called data memorization in, well, standard LLMs.
Exactly.
Can you break that down? They don't just learn patterns.
Well, they do learn patterns incredibly well. But the issue is, because they see so much data, sometimes trillions of examples, under certain conditions, they can literally just spit back out verbatim chunks of that training data.
Whoa, verbatim.
Verbatim, or very close to it. Now think about what could be in that training data.
Yeah.
Your sensitive emails, maybe, a company's confidential business plan, copyrighted texts.
Right. If an AI just blurts that out in response to some random prompt, that's a massive problem.
Huge liability, a serious privacy breach. That specific risk is what VaultGemma is fundamentally designed to prevent.
Okay, and this is where VaultGemma does things differently compared to other approaches.
Absolutely. That's where it really stands out. We've seen things like private fine-tuning. That's where you take an existing model, one that wasn't trained privately, and you fine-tune it on some new sensitive data using privacy techniques.
Okay, that sounds reasonable.
It is, but it only protects the new data you add during fine-tuning. The original model, the foundation, it might still have memorized stuff from its initial training. That risk doesn't go away.
Ah, I see. So it's like putting a privacy lock on the front door, but the back window is still open from the original build.
That's a good way to put it. What's fascinating here, what VaultGemma does, is it challenges that whole approach. It uses full private pre-training. Privacy is baked in from step one. The entire foundation is protected.
From the very beginning.
From the very beginning. It basically guarantees that no single piece of training data out of, trillions of tokens can have too much influence on the final model. It's a completely different philosophy.
That is a crucial difference. So, like you said, not just bolting privacy on, but rebuilding the whole thing with privacy in mind. And releasing this, it feels like more than just a technical paper. It feels strategic for Google.
Oh, definitely. Releasing a model like this, especially open weight, it has broader significance. It sets a new standard for what private AI should probably mean. It gives researchers a solid, reproducible baseline to work from.
It maybe gives Google some cover, legally speaking?
Well, you could see it as a strategic asset, yeah. Having a model with mathematically provable non-memorization, that's a pretty strong defense against claims of data misuse or copyright infringement down the line.
Okay, that makes a lot of sense. So we've got the why pretty clear now. But the big question for me, and probably for you listening, is how? How on earth do you build an LLM that just can't memorize? It seems, I don't know, almost counterintuitive for models trained on so much data.
Right. It does seem that way.
What's the actual technical magic here?
Well, the cornerstone, the real heart of it, is an algorithm called differentially private stochastic gradient descent. DPSGD for short.
DPSGD. Okay.
So it modifies the standard way machines learn during training. It adds two really critical privacy steps at each learning iteration. First, there's something called, per example, gradient clipping.
Okay, what does that mean in plain English?
Imagine a classroom discussion. Gradient clipping is like saying, okay, every student gets to speak, but no one can shout. We cap everyone's volume. So no single data point, no matter how unique or loud, can overly influence the overall lesson the model learns.
Okay, it keeps any one example from dominating.
Exactly. It prevents undue influence. Second, after you've averaged the contributions from a batch of these capped data points, you inject a carefully measured amount of Gaussian noise.
Noise, like static.
Sort of. Think of it as adding a subtle, random hum to the classroom discussion. It statistically blurs the individual voices just enough that you can't perfectly reconstruct who said exactly what. It obscures the individual contributions.
Huh. So clipping limits influence, noise hides the specifics.
Precisely. And this whole process, done rigorously, gives you a formal mathematical privacy guarantee. It's expressed with two parameters, epsilon and delta. For VaultGemma, it's 2.0, 1.1, and 10.
Okay, what do those numbers mean? Is epsilon 2.0 good?
Yeah, epsilon measures privacy loss. Smaller is better, stronger privacy. An epsilon of 2.0 is actually considered quite strong and, importantly, practical for real-world use. Delta is basically the tiny probability that the privacy guarantee might, accidentally fail. 1.18 to 10 is incredibly small, almost negligible.
Got it. Strong guarantee. But you mentioned something about a privacy unit.
Yes, this is really important to grasp. For VaultGemma, the privacy guarantee is at the sequence level for 124 tokens, meaning the protection applies within any single 1024 token chunk of text processed during training.
Hold on. Only in 1024 tokens. That sounds kind of short. What about longer things like a whole document or a medical record?
You've hit on a key point. That 1024 token limit is a significant constraint right now.
Okay, so if I have sensitive info that spans, say, 2,000 tokens across two chunks, the guarantee doesn't cover the link between them.
That's the current limitation, yes. The theoretical guarantee, as stated, doesn't hold across those sequence boundaries. It means if information is split, there's no formal DP promise about linking those pieces. It was likely a practical engineering choice for this first release.
Is that like a fundamental limit of DP or something they might fix later?
It's more of a complex engineering challenge than a hard theoretical wall. Extending guarantees across longer arbitrary sequences without massively increasing the privacy tax or making training impossible. It's tough.
So it's a big deal for some uses, but maybe solvable down the road.
Exactly. It's definitely a focus for future research. The tech community certainly picked up on this limitation quickly.
I bet. Okay, so beyond DPSGD itself, I read something about Google developing new scaling laws, specifically for DP training.
Yes, that was a parallel research effort and really groundbreaking.
And the finding was kind of weird, right? Something about needing smaller models and bigger batches.
Totally counterintuitive. Yeah, the optimal way to train with differential privacy, it turns out, requires a much smaller model, but train with a much larger batch size than you'd normally use for non-private training.
Why is that? Why smaller models and bigger batches?
Well, think about that noise we inject for privacy. If your batch size is too small, the noise can easily drown out the actual learning signal from the data. By using a smaller model, which has fewer parameters to learn, and training it on huge batches of data at once, you effectively average out more of that noise.
Ah, okay. The signal comes through better relative to the noise.
Exactly. It lets the model learn meaningful patterns while still keeping that privacy guarantee intact. And for you, the listener, what this means is it makes private model training less of a mysterious art.
Right. More like engineering.
Precisely. It gives people a clearer recipe, a more predictable path if they want to build these kinds of private models. It turns it into more of an engineering discipline.
That's huge. Takes away some guesswork. And they had to tweak the model architecture too, right? It wasn't just the training process.
Correct. You can't just slap DP-SGD onto any old model architecture and expect it to work well. Privacy needs to be considered in the design. For VaultGemma, they did things like drop certain normalization layers that are common in other models, and they used full attention across all 26 layers.
Why those specific changes?
These adjustments helped maintain training stability. Remember, DP training is inherently noisy. These architectural choices made the model more robust to that noise.
And the scale of this whole thing. It was massive, right?
Oh, incredible scale. They trained it on 2048 of Google's own TPU v6e chips.
Wow. So specialized hardware is pretty key here.
Absolutely underscores the need for massively parallel specialized hardware. And they use their whole internal software stack, JAX, GSPMD, the Megascale XLA compiler.
And the data, was it special private data?
No, that's interesting too. It was trained on the same massive 13 trillion token dataset used for their non-private Gemma 2 models. But crucially, it was very rigorously filtered.
So the privacy comes from the process, not curated data.
Exactly. The process guarantees privacy regardless of the input data specifics. And this huge investment, the hardware, the software, the research, it really shows Google's commitment here. They're pushing the boundaries.
Okay, so all that work, all that tech, what's the bottom line for someone, for you, wanting to potentially use this model? Because there's always a catch, right? There's this thing people call the privacy tax.
That's the unavoidable trade-off, yes. It's critical for anyone thinking about using VaultGemma. The noise and the constraints needed for DPS-GD, they inevitably mean the model doesn't perform quite as well on standard tests as non-private models of a similar size.
How big is the difference? Can you quantify that tax?
Yeah, we can look at some benchmarks. On ARC Challenge, that's a science reasoning test, VaultGemma gets about 26.45. A comparable non-private model, Gemma 3 1B, scores 38.31.
Okay, noticeable gap.
Definitely. And on Trivia QA, it's even wider. VaultGemma is around 11.24, while Gemma 3 1B hits nearly 39.75.
Wow, that's quite a difference on trivia.
It is. To give you a sense of where it lands, the researchers themselves say VaultGemma's general utility is comparable to non-private models from circa 2020, like GPT-2.
GPT-2 level, okay. So there's definitely a performance cost for that privacy.
Absolutely. And this led some people in the community to coin a term, the 5-year privacy tax, suggesting maybe private models are roughly 5 years behind their non-private counterparts in performance.
The 5-year privacy tax, that's a really vivid way to think about it.
Yep.
But here's the flip side, right? The whole reason you'd pay that tax, the payoff, actual proof of privacy. Google didn't just stop at the math, did they? They tested it.
That's right, and this empirical testing is so important for building trust. Theory is one thing, seeing it work is another. They ran really rigorous memorization tests. They took thousands of short sequences, like 50 tokens long, directly from the training data. Then they fed those prefixes into VaultGemma and checked if it would complete the sequence with the correct next 50 tokens from the training data.
What did they find?
The key finding, and it's a big one, VaultGemma showed zero detectable memorization. Zero detectable memorization, not of the exact training data snippets, nor even approximate reproductions.
Wow, that's a really strong claim. Zero detectable memorization.
It's incredibly powerful, especially for businesses, for legal teams, for anyone handling sensitive data.
Yeah, because those epsilon and delta numbers, while mathematically solid, they're a bit abstract, aren't they?
They are. They're crucial for the researchers, but zero detectable memorization, that's a message that cuts through. It directly tackles that core fear. Will this AI leak my secrets? And it provides a tangible answer.
It builds trust for using it in those high-stakes, risk-averse situations.
Exactly. That combination of the solid theory and the clear empirical proof is what makes VaultGemma potentially transformative for certain applications.
Okay, let's pivot a bit to Google's strategy here. Releasing VaultGemma, it feels like more than just a research paper drop. It's obviously great PR for them as leaders in responsible AI.
Sure.
But it also feels like maybe proactive de-risking, getting ahead of potential lawsuits or regulations about privacy and copyright.
I think that's definitely part of the calculus. It's a multifaceted move. Yes, it positions them as leaders. Yes, it potentially mitigates future legal risks. But it's also, a fantastic showcase for their whole ecosystem.
The TPUs in the software stack you mentioned.
Exactly. Their TPUs, JAX, the compilers. If you want to replicate or build upon this kind of private AI work, Google's ecosystem looks pretty attractive right now. It could drive adoption.
And releasing it open source engages the community too.
For sure. They get to influence the direction of private AI research, shape the standards, foster an ecosystem where their tools are central. It's a smart long-term play.
Right. But let's circle back to that performance gap, the privacy tax. Even with the guarantee, will that deter some of those high-value users you mentioned, like in finance or healthcare?
That's a really fair question. Is the privacy worth the performance hit? And I think for many in those highly regulated fields, the answer is increasingly yes, because the privacy guarantee unlocks use cases that were simply impossible before.
Things they couldn't risk doing with a non-private model.
Exactly. Think about healthcare. Safely fine-tuning on actual electronic health records respecting HIPAA to maybe summarize clinical notes. That was a minefield. Now, maybe it's feasible.
Okay, or finance.
Finance, yeah. Secure chatbots trained on confidential customer data,
Hmm.
fraud detection models that see sensitive transaction details, internal knowledge systems for legal teams working with highly sensitive contracts or R&D data.
Where leakage would be catastrophic.
Absolutely. For those applications, perfect privacy, even with slightly lower benchmark scores, is far more valuable than top performance with a lingering risk. Even government use cases analyzing sensitive citizen data.
So it's not about replacing the top-performing general models everywhere. It's about enabling new things.
Precisely. VaultGemma isn't trying to be the best at everything.
Mhm.
It's defining a new category. It sets a public baseline for what a commercially viable, open-source, privacy-by-design foundation model looks like. That raises the bar for everyone else.
Okay, so when something this significant drops, the tech community dives deep. What was the chatter like? Platforms like Hacker News, what were the reactions?
Oh, yeah. Hacker News had a lot to say. It was a real mix. Huge respect for the science, the technical achievement. People immediately saw the potential for sensitive research, like in medicine, as we discussed. And the self-hosting aspect got a lot of positive comments. Data sovereignty is a big deal.
But there must have been critiques, too.
Oh, definitely. The most prominent technical critique by far was that 1024 token sequence limit for the privacy guarantee.
We keep coming back to that.
Because it's a practical hurdle. As one commenter put it, if a piece of information greater than NN24 tokens long gets split, there is no theoretical guarantee across sequences. That's a direct quote. And it captures the core concern for enterprise use.
Makes sense. Any other major discussion points?
There was also quite a bit of speculation about Google's deeper motives. The usual strategizing. Was this partly to ethically justify training on free-tier user data down the line? Or was it mostly about mitigating copyright liability? The community loves to debate the why.
Always reading the tea leaves. What about the folks on Reddit, like in our local AMA, the ones trying to run models at home?
Yeah, our local AMA has a different vibe, very hands-on. Initially, there was some confusion and maybe anxiety about hardware. People wondered if you'd need TPUs just to run the model for inference, which would obviously rule it out for almost everyone at home.
But that wasn't the case, right?
Correct. It runs on standard hardware, though the requirements are still substantial for a 1B model. But for that community, the privacy tax was probably the bigger discussion point.
Because they often prioritize raw performance.
Exactly. If your main goal is getting the absolute best performance on your home GPU for general tasks, a model that's intentionally detuned for privacy might seem less appealing than a non-private alternative.
Even so, did they see any value in the privacy aspect?
The more technical users did acknowledge it. They noted that the way it's trained, with that DP noise injection, makes it statistically much harder to accidentally leak raw data, even if the formal guarantee has limits. So it's still seen as inherently safer than standard models.
And Google did make it pretty easy to get, right? It's not locked away.
No, quite accessible. It's up on Hugging Face, on Kaggle, standard formats like BF16 and safe tensors. And the license, the Gemma license, is pretty generous. It allows for responsible commercial usage and distribution for all organizations, regardless of size.
That regardless of size part is interesting.
Yeah, and Google also explicitly says they claim no rights in the output generated by users. That's crucial for businesses worried about IP ownership. It builds trust.
Okay, so wrapping up this deep dive, it feels clear VaultGemma isn't just another model. It's maybe a critical first step, a foundational piece of public research showing these large-scale private LMs are actually doable.
I think that's exactly right. It proves they're not just theoretical anymore. They can be built, they can be practical, and the privacy guarantees can be empirically verified.
So this really raises an important question then. Where do we go from here? What's next?
Well, building on VaultGemma's insights, the field has some clear directions. Number one is probably closing that utility gap. Finding new training algorithms, new architectures, ways to reduce that privacy tax without weakening the guarantees, making private models perform closer to non-private ones.
Makes sense. Well,
Second, addressing the critical limitations. Like we discussed, extending that privacy unit beyond 124 tokens is huge for real-world use. And maybe developing true user-level differential privacy, which would be even more granular protection in some context.
and you mentioned combining techniques.
Yes. Third, I think we'll see more hybrid privacy stacks, combining DP with other methods like federated learning where data stays local, or maybe using synthetic data generation. Really, this release signals a necessary maturation of the AI market. The focus is shifting slowly but surely towards AI that's not just powerful, but also safe and genuinely respectful of privacy.
A maturation. I like that. Okay, so for you, our listener, here's one last thing to chew on, a provocative thought maybe. We talked about that 5-year privacy tax, that performance gap. How quickly do you think the industry can actually shrink that gap? Can we get private AI performance close to non-private performance fast in 5 years? And maybe more profoundly, what does it mean when we can? What changes when we can confidently use AI in the most sensitive parts of our lives, our health, our finances, our private communications? Definitely keep a close eye on this space, this intersection of AI and privacy. It's moving fast,